Hello physics students. Welcome to Newton's Second Law Lab Part 1, the effect of force on acceleration. At this point, you should have already printed out pages 3 and 4 of your lab sheets in the Google Classroom stream. This is where you're going to record your data and where you're going to perform your calculations. Pages 1 and 2, the instructions, you need not print those out unless you want to, unless you feel that would be more convenient for you to do the lab. So the point of this lab is to prove Newton's second law, but actually Newton's second law is two concepts. One is more force means more acceleration, and the other is more mass means less acceleration. So in this lab, we're only going to prove one of those ideas, or we're going to try to prove one of those ideas. More force is more acceleration. And in order to prove such a statement, we have to determine forces, a bunch of forces, changing the forces every time as an independent variable, and then measuring the acceleration, the response of an object, the universe, to different forces. In doing so, while we're determining these forces and then accelerations, we can never use A equals F net over m, because then we would be creating a logical error. When you're trying to prove something, anything, whether in physics, philosophy, chemistry, medicine, you can never use the statement you're trying to prove within your proof, because then you could basically prove anything and your whole experiment becomes nonsensical. Let me give you a very simple example. Let's suppose I say to you, hey, the sky today is pink. And you look in the sky and you say, it's not pink, it's blue. And I insist it's pink. So you say, hey, this is science class. Go ahead and prove that it's pink. And I say, okay, sure, here's the proof. Ready? The sky is pink, therefore, the sky is pink. You see what I did? I used that sentence in proving what I was trying to prove. Complete nonsense. So in this lab, the challenge is to determine forces with other physics means and then acceleration with other physics means. So we're going to use force, our force unit to determine force, and then our kinematics unit to determine acceleration, and then we're going to see if they match in Newton's second law. Okay, so in order to do that, rather than using the equation as I mentioned, I have this setup over here. It's a track, a car with nice low friction bearings so the wheels turn very easily, and a string and a pulley and a motion detector like we used in the graphing activity. The difference being that instead of using a computer, we're going to use a Texas Instrument calculator to determine our motion graphs. Now, the first thing that I need to do is eliminate all other effects in the experiment. Because remember when we were starting graphing motion and I came up in the notes, I was showing you this example where I said, imagine we did an experiment and we wanted to see how eating donuts affects body weight. So we start eating 6 donuts a day. And then we do this experiment and we find that we're losing weight. And then we can conclude erroneously that, hey, eating donuts makes us lose weight, failing to make a note that at the same time we began our experiment, we entered into the military and we went to boot camp. And we were running miles and miles a day, carrying logs on our shoulders, running up hills, climbing ropes. And so that was responsible for the weight loss. So when you're trying to do an experiment like that, you have to just change one thing, eating donuts, and keep everything else constant. And so in this experiment, the idea is the same. When we're varying force, we have to eliminate all other influences on this system. So I have this thing, I'm going to pull it across the table, but if you notice, when I let this go, without any force, it starts to accelerate towards the motion detector. And the reason why is because the ramp is tilted this way. So first thing I have to do is level the track. There's a screw at the end here. By turning it, I am raising this end of the track, so this is no longer downhill. I'm picking it up to try and make it level. Now when I tap like this, and I see that it doesn't favor any particular direction more than the other, it's now level. But what I'm going to do is I'm actually going to go a little bit higher and tilt this up, because even if I make this perfectly level and I tap like this, friction is also present and eventually stops this car and causes an acceleration even though I'm not putting any force. So I'll go a little bit higher and make this a slight downhill so that when I tap this, the car more or less rolls at a constant velocity down the ramp. I don't want it to accelerate. I just want the hill to basically cancel out the minuscule amount of friction in these bearings. This is looking pretty good. Okay, it doesn't have to be perfect, but we want this to roll at a steady pace, and that looks about right. Okay, so there. Now I've eliminated friction, and now what I'm going to do in this experiment is I'm going to hang a mass over here on this pulley, and that will create a force, which then produces an acceleration. If you go like this, you see the car is accelerating. So the force is actually coming from this metal block, and there's a word we use for the kind of force it is. And I'll give you a hint. What do we call that force when something I let go and it pulls down? Okay? Let me pause for a little bit and give you a chance to think about. It's one of the 4 forces we studied in Unit 1. Okay, hopefully you said the force of gravity, okay? So the force of gravity on what? Not the car, because that's held up by the track. Only the force of gravity on this little pulley is what makes the car accelerate forward because of the pulley and the string, it pulls it forward. So I could measure the acceleration here with a motion detector, and I will. But first I want to just talk about the big idea of this experiment. So I get a force and an acceleration. So far, so good. Now what I want to do is see if more force makes more acceleration. So rather than this 10-gram mass, I'm going to take this off and put on 20 grams, which will now be more gravity and therefore more force, more acceleration. So when I let this go, we will see, you could see it with your eyes probably, but we'll see it with a motion detector to measure it numerically that indeed with more force there is now more acceleration. And we're going to proceed with 20 grams, 30 grams, up to 80 grams. Keep increasing the acceleration, keep increasing the force, and keep increasing the acceleration as a result. But here's the problem. Remember that jelly donut example I said, if I'm eating donuts, I can't go train boot camp at the same time because I'm introducing 2 factors into my experiment. And what I am doing when I put this 20 is I actually increased 2 factors, not just the force. What used to accelerate was the car, which is, I'll just make up a number, 200 grams. Plus the 10, what accelerated here was a total of 210 grams. Then, if I take this off and I go like this, and I let this go, what's accelerating now is not 210 grams, but 220 grams. Then I go like this, and now 230 grams is accelerating. And what I'm doing is I'm changing both the force and the mass, which makes an invalid experiment. You got to keep everything constant. So if I want to test only the force, I've got to figure out a way to keep the mass of the system constant. So there's a little clever thing we do. We take a bunch of masses and we put them on the car. 2 200s, 2 20s, and a 50 gram. Okay, so now I have all these masses on the car. What I'm going to do is I'm going to let this go, and I'm going to get the motion detector to measure this acceleration. So I've got a certain force, a certain acceleration. Now what I want to do is increase the force without increasing the mass. So what I'm going to do is rather than take this off and put it on the table, which will make the system lose 10 grams of mass, I'm going to put this 10 grams on the car so the system is not losing any mass. Then instead of grabbing a new mass and putting it over here, which would increase the mass of the system, I'm going to take this off so the car loses 20 grams, but the pulley gains 20 grams and the system is still constant. So then I'll go like this, tick, 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 tick. Motion detector determines the acceleration. And then for 30 grams, to keep the system constant, I'm going to take the 10 off the car and put it over the pulley and the system is still constant. 40 grams, I'll go like this and like that. So notice what I'm doing, the general, if I could just say in general, any mass I take off the pulley goes back to the car. Any mass I add here came from the car and the system remains constant. Okay, so that's the thinking behind this experiment. Let's now go ahead and take some data. So the first thing I'm going to do, I'm not going to read you the procedure, but I am on step 1. I'm going to put the car and everything on an electronic balance, and I'm going to record that. So students in class struggle because the car has wheels, rolls off. You could flip it over to keep it on the balance, put everything on, and now my system has a mass for me of 758 grams. So I'm going to write that down on my data sheet right here. Okay, so you're not going to write this number down because I'm going to give everyone their own data in a Google Sheet. But you see, here's the mass of the car, 758 grams, and then I converted it to kilograms because I'm going to need the mass in kilograms later in the lab. So that's basically there, all right? Again, you will look in your Google Sheet to get the data. So go ahead and find that now. Okay, so next thing I'm going to do is I'm going to set my system back up and get it ready to accelerate. Oops. Okay. And maybe I'll put this here to keep the car from moving. All right, so I'm starting with 10 grams over the pulley. So now I'm going to turn on my motion detector, my calculator. So we should hear the Lab Pro turn on. The bottom piece here is what communicates with the motion detector. And then I'm going to start a program that's going to run on the calculator and control this, what we call a Lab Pro. Okay, so we're ready to take data with 10 grams hanging over the pulley, our smallest force, and the motion detector will now determine the acceleration. Here's the thing, with these sound clicks, you can't hold your hand here and go like this. The sound is going to be reading my hand and not the car. So I got to keep my hand out of the way. That's why I'm going to put my finger like this. And when I let go, I'm not going to push the car. I'm going to pull my hand away like this. And then I'm going to stop this from flying off the table because this car is actually about $50, so I don't want to launch it off the table. So that's basically the experiment of how we collect data. So let me initiate this motion detector, and as soon as I hear ticking, I know it's recording the motion of the car. I'm going to let the car go and allow it to watch the motion and measure it. Okay. Okay, so the motion detector recorded the data, and we got to let it process for a little bit. So while it's processing, I just want to show you something. I'm skipping a little ahead in the procedure, But that's okay because we have to do things a little bit different because this lab is done virtually. So I've filled in the force column here, and I'm not going to tell you how to do this, but you have to think about, first of all, the conversion to kilograms. That's straightforward. That's something you were doing in lower science classes. It's just a conversion of taking 10 and turning it into kilograms. Notice I don't need the units because it's at the top of the data table. But somehow I take this and I have to figure out the newtons on those kilograms without using A equals F over M or F equals MA. I cannot use that because I'm trying to prove it. So something with this number, I have to do a calculation to figure out the force over the pulley. What is that force? Well, I mentioned it earlier, but you should understand that it is a force from among the forces we studied in Unit 1 forces. I'll give you a hint. If I let this go, right, so why is that falling and hitting the clipboard? For the same reason it pulled the car across the table. And that force has a name to it. Again, it's not a spring force, it's not a normal force, there's a name to it. We studied it in Unit 1. And when you know the mass and that it's that kind of force, there's a formula on the reference table that allows us to calculate this force. So the rest of these I'm going to leave for you to do. But here's your hint. If you do it right, you should get 0.098 if you follow the correct process with 0.01. And then you do these conversions, and then you do the conversions and fill in the rest of the data table. But now the acceleration. Well, that's the dependent variable. This was the independent variable. This affected the acceleration. How do we determine that? Well, the motion detector does it for us. Notice we've got a parabola here. That's because we have displacement over here and time over here. And that graph is a curve when something accelerates, and of course our car did accelerate. Now, just so you see that it's a curve, I put a piece of paper there. You could definitely see that that's not a straight line, that is a curve. So we need to find the acceleration of this. But the slope of a displacement graph is the only thing we know how to do, and that gives us velocity, not acceleration. The graph that gives us the acceleration, if we calculate the slope, is the velocity graph. So that's what I've got to do. I've got to switch this motion detector, this calculator, to show me the velocity graph right here. So I'm going to switch down here through the menus, hit enter, and now it's going to plot the velocity graph. Now you see a linear graph just like we studied in the kinematics unit. We need to get the slope of this line. So what I'm going to do is the calculator can do that for me. I'm going to go to fit over here. This would all be in the instructions, but I'm doing it for you. So the first power, because we know it's a straight line, a second power is a parabola, a third power is another curve. To the first power, when functions are to the first power, they make straight lines. So that's what I want. I want a curve fit with a straight line. So this instruction says, move the cursor to the start of the trend region. That's right around here. That's when the car begins to accelerate. And then I hit enter. And now it says move the cursor to the end of the trend region. So I'll move it to right around here, maybe somewhere around there. The end looks like some kind of little bump. So now I'm going to wait while the calculator calculates the slope of that line. The slope of the velocity graph is the acceleration. So there it is. I don't know if you could see it, but what I do with my data now is I write down this A, which is the acceleration of 0.11. And I only need two significant figures because I'm ultimately going to graph those accelerations, and the graphs won't be very precise because I gave you the axes. So what I did is I now jotted down my acceleration of 0.11. Again, this is determined from force calculations. This is determined from the motion detector and kinematics and slopes. I never use F equals MA to find either of these. So now I'm in a position to measure more of these and see if F equals MA or A equals F net over M is true. So I got my first piece of data. Time to get my next force and my next acceleration. I want to increase the force and see if the acceleration increases. So let me bring this back to the starting position. And now I'm going to take off the smallest force and increase because I took 10 grams off and I'm going to put 20. So I'm going to have more mass and therefore more weight, which should see more force, more acceleration. So increase the force. Let's get the motion detector to now record the motion and see if we get more acceleration. Okay, and I stopped the data taking. Again, we have to wait for the data to process in the calculator's memory. And there we get our nice parabola, d equals 1/2 at squared. Again, to get the acceleration, we've got to look at the velocity graph. So, the velocity graph is here. Once again, we see a nice linear line because the velocity is increasing. The slope of this line gives us the acceleration. So we go through our menus, we go to the first power, plot, hit enter. Again, that's going to calculate the slope of a straight line, first power. I move the cursor to the start of where the car begins to accelerate. And then I move it to the end, which is up over here. And now the calculator will calculate the slope of that line. Okay, and there it is. I see 0.24. So I write that down in my data table right here. So there we are. Once again, you're not writing these numbers down. You're going into the Google Sheet and getting your own data. But that's what we see. We do, in fact, see more force, more acceleration, which is good. The pattern is showing up. Again, this you're going to figure out by yourself. So we got our next piece of data. Now what we need to do is move on and get the next acceleration. Okay, so that was 20 grams hanging over. Now we want to increase to 30 grams to make more force, more acceleration. So I'm going to take the 20 and add to it the 10. Now again, 30 grams is not the force. Force is in newtons. That's something you're going to have to calculate without using A equals F net over M. So I've got my car ready to go, and let's get the motion detector to record that acceleration. Okay. Okay, I stopped the data collection, and again, we've got to wait for the calculator to process the data. Again, the displacement versus time graph is a parabola because it is accelerating. We've got to look at the velocity graph to calculate the slope and therefore the acceleration. Once again, we see a nice linear rise. We've got to get the slope of this line as the car is speeding up, velocity is increasing. So we go into our menus, fit to the first power, move to the start of our linear range, maybe, well, I guess maybe right here is safer. Hit enter, go to the end of the linear range, hit enter, and wait for the calculator to calculate that slope. Okay, I see about 0.37 for an acceleration. So I'm going to fill that in on my data table in the third place right here. Okay, again, we see more force, more acceleration. Good. It looks like we are indeed proving Newton's second law. But again, you're not jotting this down. You're getting your own data from the data table. Notice we about doubled the acceleration, then we about tripled the acceleration because we were doubling and tripling the force. So we should see a nice proportional pattern just like in Newton's second law. So we just did 30 grams. Now it's time for 40. I achieved 40 by taking the 10 off, returning it to the car, and to this 20, I'm going to add another 20, so now I have 40 grams hanging over the pulley. So I got the car ready to go in its starting position. Let's initiate data collection. Okay. Okay, stop the data collection. Again, let's wait patiently for it to process the data. Again, we see a nice parabola for the displacement graph, so everything looks good, but we've got to look at the velocity graph to calculate the slope, because the slope of a velocity graph is acceleration. We see a nice straight line, so we get the calculator to calculate the slope for us. Let's tell it to start right here. That's about where the acceleration begins, and it ends about there, so we'll tell it to stop there. Give it a moment to calculate. And I see about 0.505, which I'll call 0.51 for the acceleration. So again, I put my number there. You're going to look into the Google Sheet for your own acceleration for this trial run of 40 grams. So that was 40 grams. Now let's move on to 50 grams. So to the 40 already hanging, I'm going to add another 10. Now I got 50 grams hanging over here, and we should observe even more acceleration. So let's get the motion detector started. Okay. Okay, I stopped the data collection. Again, we give it a moment to process the data. See a nice parabola again. Again, that doesn't help us find the acceleration. What we need is the velocity graph so we could calculate the slope. Nice linear region, the velocity is increasing. We've got to get the slope of that to get the acceleration. We fit to the first power because it's a linear graph. So I move to the start of the trend region, maybe around there, and the end of the trend region, maybe it's around there. So let's give it a moment to do some calculating. And I see about 0.646, which I'm going to call 0.65 for the acceleration. So here is my 50-gram trial run, and it's 0.65. Again, you're not writing that down. You're going to look in the Google Sheet for your own acceleration. So that was 50 grams. Let's now move on to 60. So what I'm going to have to do is take off all of these except for the 10 and add 50. So I have 50 plus 10 is 60 grams hanging over the pulley now. And let's get the car in the starting position right here and initiate data collection. Okay. Okay, I'll stop it and give it a chance to process. Again, a nice smooth parabola, d equals 1/2 at squared, but that doesn't help us. We need the velocity graph so we could calculate the slope and therefore the acceleration. So we're again going to fit to the first power because it's a straight line. We move the cursor to here. That's about the start of our trend region. Let's move it to the end of our trend region. We'll give it a moment to calculate the slope. And I see about 0.756. So we can call it about 0.76. Okay, so I write that down in my data table. Again, you're getting your value for 70 or 60 grams out of the Google Classroom sheet that I'm going to post with this assignment. That was 60 grams onto 70. So to achieve 70, what I'm going to do is take the 10 off, so I'm back to 50, and now I'm going to add 20 grams. So I have 70 grams hanging over the pulley. Got the car in the starting position, and let's start the motion detector. Okay, I'll pause, stop the data collection. We'll wait a little bit, allow it to process. Again, a nice smooth parabola, so we need to look at the velocity graph to calculate the slope of the velocity graph, which will be the acceleration. So we go and ask it to do a first power fit. We move the cursor to the part where the object begins accelerating. Well, looks like in between there. Yeah, maybe right there is a better starting point where it truly becomes linear. And then we move to the end. Give it a moment to calculate the slope and therefore the acceleration. And I see about 0.891, so I'll just call it 0.89. Okay, so I write that down. For the 70 gram hanging over the pulley, my acceleration of 0.89. Again, you're getting your value off the Google Sheet in the stream. That was 70. One more to do, 80 grams. So to achieve that, I'll take 10 off the car and add it to the 70 already hanging over the pulley. So now I have 70 plus 10 or 80 grams. Okay, so this should be our most rapid, our largest acceleration yet. I've got the car in position, and let's start the motion detector. Okay, I'll stop the data collection. Once again, a nice parabola. We need the velocity graph, though, to get the acceleration, so let's look at that. A nice linear trend right there. Let's get the calculator to calculate the slope of that. I'm going to move to the start of the acceleration, maybe right around there, and then the end of the acceleration right around there. Let's give it a moment to calculate. And it reports a slope of 1.03, in other words, an acceleration of 1.03 meters per second squared. I put that in for my last entry into the data table. Again, you're getting your value from the Google Classroom stream. So that's it for data collection. Okay, so here's all my data. Again, you're getting your own from the Google Classroom stream and that Google Sheet. And at this point, I've done the procedure for you, but in the data analysis, we are on step 14. So this is now where you're going to want to follow the procedure from here on. Of course, I'll do it with you, but you're going to want to read carefully also as you're working through this lab. So the first thing, step 14, convert all the mass hanging over the pulley to force. In parentheses, if you don't know how to do this, comb through the mechanics section of your reference table. So what do I mean by that? All the mass hanging over is right here. You've got to convert it to kilograms, as I mentioned, and then you've got to convert that to newtons. I did one for you. You have to find a formula on the reference table to turn this into that, okay, but for all these data values. So that's that. Now, step 15. Plot your data on the graph provided. Since force is the independent variable, it belongs on the bottom axis. And then here it tells you how you're going to be graded, that your axes are scaled properly, your axes, your graph has all the labels, you know, the titles and all on all the axes. 2 points for all your data accurately plotted, and then 2 points for your best fit line, that it's straight and reasonably placed. So I plotted the points here. But now, and notice I've got all my labels and all that. You have to do the same for your data. The best fit line, as always, as I say, can be a little tricky. So what you're going to do, what I recommend is take these. I put them in pencil, but I'm going to take, you could take a pen. Well, this marker's kind of a little crude, but I'm going to just dot these lightly. With a pen, you could color these in so that in case you mess up on your best fit line, you can erase and your points won't disappear, and you could try again. So there are my points dotted in ink now. So next thing I'm going to do is, remember, for best fit line, what you have to do is you have to put the ruler down once and draw a nice line that goes through the center of the trend. This is going to be a little bit awkward for me because I have to have this tilted up against some books on a table like this so it's visible for the camera. My best fit line might not be great. but me leaning over because the tripod's in the way too, it's going to be a little awkward, but your best fit line will be perfect, right? Because you'll have none of those restrictions. So I think this is, oh, let me go like this because the clipboard now is in the way too. Maybe something like that looks pretty good. So I will, okay. Actually goes through most every point anyway. So there's my best fit line. So now step 16, that 16 was the best fit line. 17, determine the slope of your best fit line with units. So remember, slope, you always have to start with an equation with all calculations. So I'm going to do slope equals, oops. Now I could say change in y over change in x, or I could say change in acceleration over change in force. Either one is fine, but that's what I have on my y and x axis respectively. So what I'm going to do now is pick some points. Let me just see if I'm still on the camera view. Yep, still good. Okay, so I'm going to pick the beginning and the end of the line. That's what I recommend. Pick points as far apart as possible. So the change in acceleration, it goes from 0 up to 1.2. So 1.2 meters per second squared minus 0 meters per second squared. And then the horizontal change, the change in force, it goes from 0 to, looks to me, about 0.92. In other words, the change is 0.92 newtons, the final, minus the original 0 newtons. Now, here's my calculator. Okay, now I'm going to just do that 1.2 divided by 0.92. Of course, your answer is going to be different because you have different data, but what I got is 1.30. And then, now, what are the units? The easiest thing to do is just leave all the units of the line above. Meters per second squared on the top and newtons on the bottom. That looks funny probably. You're thinking, what a strange set of units. Isn't there some way to simplify that set of units? There is. We're not going to bother because in the Regents, any set of units that's actually equivalent to the so-called correct set of units is correct. So what I recommend, if you're not sure what the units are, just keep all the units of the line above just like that. Okay, so you're going to do this similar calculation with your data and your best fit line. Everyone will have most likely a different slope there, but that's how it is calculated. All right, so moving on. In the analysis 18, now inspect your graph with a mathematical mindset. It will allow you to determine part of Newton's second law, which of course is A equals F net over M. Noting the mathematical pattern illustrated by the variables, explain how the graph shows that F belongs in the numerator of Newton's second law and not in the denominator. In the process, also state what the graph would look like if F was in the denominator. So, what does all that mean? Well, if you look at that graph, it shows a pattern of increasing. Okay, so it does show more forces, more acceleration. But if you didn't know that, you didn't know any physics, how do you know force? This variable belongs in the numerator of an acceleration equation. Let me just kind of give you some pointers. What if you had a function y equals x over 1? If you drew a graph of y and x, what would that pattern look like? How would you draw that? Okay. Or what if you had y equals 1 over x? If you're not sure what those look like, try it on your graphing calculator. Try this, put it in the function, and plot it, and sketch in what you see, Try this, sketch in what you see. Then go back and look at what you see over here in your experiment. Which one does it look like? That's how you answer the question. But remember, there are a couple questions embedded in this question. It says, explain how you belong in the numerator. It belongs in the numerator. And then this, in the process, also state what the graph would look like if f was in the denominator. So you're going to need at least 2 sentences to answer this. Why does it belong in the numerator? And then if it did show up in the denominator, what would the graph look like, which obviously is not what we have. So that's how you answer 18. Okay? Moving on, 19. Next, explain how your graph shows that the law is a equals f over m and not f squared over m or f cubed over m. Make sure to also state what the graph would look like if Newton's second law was f squared or f cubed over m. Not sure how to answer that question? Again, look at this and then use your Texas Instrument calculator to help you. Try this. Y equals x over 1. Plot that on your calculator with y over here and x over here. What does that look like? Then try y equals x squared over 1. Plot that on your calculator. See what that looks like. Try this on your calculator. Fill in these on a piece of scrap paper. You'll see different shapes depending on whether it's x to the 1 power, x to the 2 power, or x to the 3 power. Then look at your graph and explain why it matches x to the 1 power based on shape alone. And so in question 18, we knew that we answered why it belonged in the numerator. And then in question 19, you're going to answer, well, how do we know it's to the 1 power and not squared or cubed? So see, we're figuring out Newton's second law only from data. Okay, number 20, probably the trickiest part of the entire lab. That's why it says the tricky part. Okay, so here's what it says. So you have demonstrated with your data that f to the 1 power belongs in the numerator of Newton's second law. Now you will use your graph to determine the mass of the accelerating system. To do this, now you can finally assume that a equals f net over m. Using only your slope and this equation to guide your reasoning, calculate the mass of the car, the string, and the masses you used in your lab. Somehow the slope is related to mass. Okay, this is, as I said, pretty tricky. So notice when we go back and look at the slope, it has meters per second squared on the top for units and newtons on the bottom. In other words, oops, sorry about that, people. I just realized I made a mistake. I don't know why they called this A, but it should be slope. Maybe you're going to need a little white out, or if you use the pencil, you can erase that, but I apologize for that. So that's the slope. All right, so the slope was meters per second squared over newtons. In other words, meters per second squared is an acceleration, newtons is a force. So that's what we got when we divided 1.2, or when I divided 1.2 by 0.92, I got acceleration over force. What does that equal? Well, here's the equation according to Newton, and I'm just dropping the F net just to make it a little simpler to write. What I want to do is have A over F on this side to see how the slope relates to mass. What I can do is multiply both sides by 1 over F. So on this side, I have A over F, which, as we know, is equal to our slope, as we see over here. On this side, what do we have? 1 over M. So basically, our slope is 1 over mass. the reciprocal of mass. That's what we just determined. In other words, if I go back here, and if I took my 1.2 and I divided it by 0.92, that gives me 1 over mass. What can I do instead with these same exact numbers to not get 1 over mass, but get mass alone? Okay? I did 1.2 divided by 0.92 to get reciprocal of mass. What do I do to get mass with these two numbers? That's what you do in this box number 20 again. Okay, so that is right there. With your two numbers, figure out the mass, calculate it, and show the calculation and put it in that box, divide it out, and give me the kilograms. Okay? So that's number 20. And then moving on, 21, calculate the percent error between the mass determined in step 20 and the measured mass of the car. Consider the mass from the balance, the accepted value. So you're going to get a number here, some number of kilograms. You're going to compare it to this number of kilograms. All the way back in the beginning of the lab, the first thing I measured was this. Again, you got this off the Google sheet. Take this number and compare it to this step number 20. Calculate the percent error. Okay, so that's what you do there. Okay, 22. This is now the concluding statement of the lab. So this actually is also a bit on the tricky side. You have to answer, and a lot of people just answer this with a quick sentence and they finish, they lose 3 out of 4 points. This is 4 points. Answer the following. Did the lab prove A equals F net over M? Hint, no it didn't. I gave you the answer right there. So you start right with your 22. No, it did not prove A equals F net over M. But you have to go more. Explain why it didn't. And here's another hint. Two things affect acceleration according to Newton's second law. What are they? And how do they affect the acceleration according to theory? So you answer what those two things are. There's 2 points, 2 sentences. One thing that affects acceleration is, and then you explain it. The other thing is, and then you explain it. So 2 points. And then here's 2 more points. Which of these relationships did this experiment prove? And which did it not prove? So you're going to say the 2 things, and you're going to say, this experiment proved the relationship, blah, blah, blah. It did not prove, blah, blah, blah. And there's your 4 sentences. Note your answer here should have 4 statements. Okay, so there's 22. And the last thing, 23. Somewhere in this lab, I used the physics concept term incorrectly. Identify the misconception and explain how to correct it. So what I'm talking about is in the procedure, steps 1 through 13, I used the physics word incorrectly. This is actually another pretty tricky thing. And so what I'm going to say is this year, I'm going to make 23 a bonus. Okay? So it's a bonus question. If you can't get it, I'm not going to give hints. Take a guess. You might get a point or not. If you get it wrong, nothing to stress about. Okay, so that's it. That was the experiment, Newton's second law lab part 1. Hopefully you proved that more force equals more acceleration and also to the first power. So I hope you enjoyed the lab. The next lab we'll be doing is part 2 of Newton's second law, testing the relationship of how mass affects acceleration. So I'll see you in that next lab.